Hello everyone, welcome to the week 2 of ITE 2232 Computer Networks and Operating Systems course. Last week we discussed about an overview of the operating system when we talked about the major components of the operating system and major responsibilities of the operating system. In this lecture, we will discuss another important topic of operating systems, which is about processors and threads. As usual, we'll be using the color coding system to highlight important points. Here is the agenda for this lecture. First, we will talk about processors and major components and the characteristics of processors. Secondly, I will introduce you threads, which are some sort of lightweight processors, and let's see how the characteristics of processors versus threads. Then we will talk about how to map threads with processors and certain other related technologies. When it comes to the responsibilities of an operating system, application execution management is one of the major tasks that the operating system is responsible for. The resources of the computer system, that are processor, the memory, the input-output devices, they are shared with all the applications, so all the programs of the computer system. And it is the responsibility of the operating system to make them available to these multiple applications. The processor is switched among multiple applications so that as users, we will see that they are smoothly working in the system. What actually happens is they take turns taking the control of the processor. So we will see, due to this behavior of application execution management conducted by the operating system, that the multiple applications running on the computer are progressing. The processor and I/O devices can be efficiently used due to the application execution management schemes performed by the operating system. Now let's talk about processors. I briefly introduced processors in the last lecture as well. Today we will go into a bit of depth about processors to understand what exactly a process is and what are the characteristics of the process and what are the requirements and the objectives that we achieve using processors. The process is the basic management unit of the operating system. It's probably the most important data structure of the operating system. This process contains the program code that may be shared with other processes that are executing the same program and the data associated with the program code. So like I explained in the last lecture, a program, when it is not executing, it's a program code. When it is executing, it's a process. So for the operation of a program, we need both instructions and data. So the process is associated with both the program code and the data associated with the program code. When the processor begins the execution of the program, we refer to that as an executing entity. In other words, as a process. A process consists of these items at a high level. It has an identifier, a state, a priority level, a program counter, some memory pointers, some data, some input-output information. What are the input-output devices that are associated with that process, and some accounting or logging information. This is how the process control block looks like. So the process control block is the data structure that holds information about a process. So the components or the characteristics that I mentioned in the earlier slides, such as the identifier, the state, priority, those things are actually stored in this process control block. The process control block is actually saved in the memory. For each process, we have a specific, so each process has a process control block of its own. So this process control block, this data structure, is the key tool for enabling multiple processors at the same time that can use the processor. Process control block also facilitates swapping processors in and out of execution. So what does it mean by swapping processors in and out of execution? Is that the processor, being a scarce resource that we have only one processor or few processors in some multiprocessor systems. If we consider a uniprocessor system, we only have one processor, right? But we have multiple programs that want to run in that processor. So we need to take turns taking the control of the processor. So this process control block helps us switch the one process and give control to the other process. So this process switching is called swapping of processes in and out of execution. Process control block is created and managed by the operating system. Now, let's talk about the states of a process. Before we go into states, there are two important components that we need to understand. One is the dispatcher. So dispatcher is a small program in the operating system that switches the process from one process to another. Switches the processor from one process to another. That means, like I explained, we have multiple programs or applications that want to use the processor. So the dispatcher is responsible for dispatching certain instructions in a way that the processors are switched and they take turns to use the processor, the system. The trace is the behavior of an individual process by listing the sequence of instructions that execute for that particular process. The behavior of the processor can be characterized by showing how the traces of the various processes are interleaved. So you will see some example. In the process execution, this is the memory layout for three processes: process A, process B, and process C. And you can see that the address range starts from 0 and dispatcher is at the address 100. So it is actually another program, but it has a special purpose. Process A, B, and C could be user processors, and they have starting addresses of 5,000, 8,000, and 12,000 respectively. So, and you can see the program counter, the register that identifies the next address that needs to be fetched or executed. It's indicating 8,000 in this example snapshot. So the dispatcher is there to switch processor from one process to another. For example, from process A to process B, and process B to C and C to A or B, is that switching is conducted or performed by the dispatcher. So I talked about the traces. The traces include the series of instructions and the addresses that one process consists of. So the process A started at address 5,000. So you can see what are the addresses that are associated with the process A, 5,000 to 5,011. Then process B starts at 8,000 and it goes until 8,003. Then process C from 12,000 to 12,011. Now, when these three programs A, B, and C are executing on the processor, let's assume that the execution starts with process A at the address 5000. So you can see from 5000 to 5005, it executes, and there's a timeout. So that means the specific time allocated for that program is over. Right? That's the timeout. Right? So actually, in this case, you can see the processor is only executing half of the process A trace. So the process A trace starts from 5000, goes up to 5011. But if you can see the execution trace, it's only going up to 5005, and there's a timeout. So this timeout occurs due to some time quantum or time quota given to the program by the operating system. So each program can only run within its time quantum. So you will see more when we discuss about scheduling in the next week's lesson. So once the time quantum is expired, then we encounter timeout. The dispatcher is actually running. So you can see the dispatcher code starts at 100 according to this memory layout. So after 5005, then we have 100 running. So that means the dispatcher code needs to be executed on the processor to give space to or do the switching process to the next program. So after that, you can see process starting with 8000. So that is process B is executed. So at 8003, you can see there's an IO request, and when the IO request occurs, there is a blocking phenomenon. I mean, IO request takes more time. So instead of waiting for the IO request to complete, the dispatcher comes and gives processor to another program. So now the dispatcher gives chance to address 12,000, which is the process C. So after running the process C for some time until the 28th line, you can see 12,005, there's a timeout, and then the process stops or pauses, and the chance is given to process A again by the dispatcher. So you can see address 5006 to 5011 are executed, and there's a timeout, and then again the dispatcher comes into the execution and gives chance to address 12006, which is the process C. So this is an example of how different programs are switched on the processor by the dispatcher. So the exact order of execution of the programs, or how these are switched, how long would one program get, all of these are determined by some scheduling algorithm which is implemented on the operating system. So in this lecture, we will not talk about scheduling or scheduling algorithms. You will learn about that in the next week's class. Talking about the processors, as you can see, the processors switch between two states mainly, the not running state and the running state. So this is a very simplified way of looking at processors. So when the processor is ready to be executed, it enters the not running state, and then the dispatches it on the processor, so it goes to the running state. And when there's a timeout, or when there's a IO blocking call, the running state now is suspended and it goes to the not running state. So in the two-state model, so you can have different process models to explain the behavior of a process. Right, two-state model is shown here. You will see some other state models as well. In this model, which is very simple, we have only two states: the running state and the not running state. So the not running state, after dispatching, goes to running state, and when it is paused, it goes to not running state. And once the process execution is completed, exits the model or the processor. So in the two-state process model, the queuing diagram looks like this. You enter a certain queue and the dispatcher takes the process from the queue and dispatches onto the processor. And this cycle continues until the process is completed. So when is a new process created? When there's a new batch job, the operating system is provided with a batch job control string, usually on a tape or a disk. When the OS is prepared to take on new work, it will read the next sequence of job control command. So when a new batch job is provided, then the OS creates a new process. Interactive logon, a user at a terminal logs into the system. So when you log into the system, it could be a web-based system or any system, a new process will be created to handle that user. And then processes could be created by the operating system to provide some service. The operating system can create a process to perform a function on behalf of the user program without having the user to wait. For example, a process to control printing. Or the processes could be actually created by existing processes in the system, which we call as spawning. So spawning means for the purposes of modularity or to exploit parallelism, a user program can create a number of processes. So we call them the child processes of the process that these processes are creating. So process spawning is when the OS creates a process at the explicit request of another process. So we have, then in that case, we have a parent process and a child process. So parent process is the original process that requests the OS to create a new process, and the process that is being spawned, or the newly created process, is called the child process. And the process termination can happen due to various reasons. One is the normal completion of the process. The process executes an operating system service call to indicate that it has completed running when it is normally completed. When the time limit is exceeded, for example, the process has run longer than the specified total time limit, there are a number of possibilities for the type of time that is measured. These include total elapsed time, amount of time spent executing, and in the case of an interactive process, the amount of time since the user last provided any input. So there could be some timeout which will trigger the process termination. And the processes can terminate when there is not sufficient memory available in the system. Also, when there is a boundary violation, the process tries to access a memory location that is not allowed to access for that particular process. In that case also, process may be terminated. When there is an error, the process may be terminated. So there could be some protection errors, there could be some arithmetic errors. Then the process can terminate when there's a time overrun. The process has waited longer than the specified maximum period for a certain event to occur. When there's an input-output failure also, the process can terminate. Also, there could be instruction-related issues such as invalid instructions, trying to execute privileged instructions that are reserved for the operating system. The processes can terminate. When there's a data misuse, such as a piece of data of the wrong type or not initialized data is going to be used by the process may be terminated. Process may be terminated by the intervention of the user or the operating system as well. For example, if there's a deadlock, you will learn about deadlocks in future weeks. So for some reason, if there's a deadlock, like 2 or more processes are waiting in a deadlock, means they're not doing anything useful, they're just waiting for another processor's action. So in that case, to break the deadlock, you need some external intervention, often by the operating system or the user. Then the parent termination. When the parent is terminates, the operating system may automatically terminate all the offspring of the of that parent process. So this is happening when we have one process creating or spawning many child processes, and depending on how it is implemented, when the parent terminates, the operating system may automatically terminate all of the child processes belonging to that process. And also, when the parent process requests, the process may be terminated. The child processes may be terminated. Now, let's look at a bit more complex state model for the process life cycle. Now, this is a 5-state process model. So, in this case, there are 5 states, namely new, ready, running, blocked, and exit. So you can see how these are interrelated. When a process is newly created, it is at the new state, and it is admitted to the system. It goes to the ready state. It's not running yet, it is at the ready state. So all the processes at the ready state can be dispatched and can be transferred to the running state by the dispatcher. So when there's a timeout, natural timeout, that means the time quota that is given to the process exceeds or it completes, then it has to go to the ready state again. It's different from blocking, in which the blocking state occurs when there's a waiting event, such as IO operation waiting or some blocking operation. From the running state, it has to go to the block state, because if it goes to the ready state, if there's nothing else in the processor, it should be ready to run. But in the case of a blocking event, if, for example, if the process is waiting for some input from the user, if the input is not there, then although it is at the ready state, you cannot run. So it actually has to go to the block state when there's a waiting event. And when the event occurs, it goes back to the ready state, and the dispatcher can put it into the running state. Once everything is completed, the process is released from the processor, so it goes to the exit state. So this is how the 5-state process model works. So you can see this is more comprehensive explanation of the process life cycle than the 2-state model. Here is a depiction of 3 processors taking turns on the processor. So the timeline, you can see the dispatcher comes into play once in a while. So process A runs for some time, and then it goes to the ready state. And process B then is brought into the processor by the dispatcher, and it is blocked after some time. And the process C, which is at the ready state, now goes into running state, and then to ready state again, and then running state again at the end after process A completes. So this is some example of how the different processors having taking turns on the processor to run. So when none of the processors in the main memory is in the ready state, the OS swaps one of the block process out onto the disk into a suspend queue, right? And then the OS brings in another process from the suspend queue, or it honors a new process request. So this is how the it's some more explanation to the timeline we just saw. Swapping, however, is an IO operation, and therefore there is a potential for making the problem worse, not better, because this IO is generally the fastest IO on a system. Swapping will usually enhance performance. And so when there's a when there are no processors in the memory that are in the ready queue, the operating system can bring in some new process from some suspended queue. If there's a suspended queue, so because the process is actually idling, and the current processes that are scheduled on the processor cannot run due to the block state. And this is what the suspended process is all about. So in that case, we have a new state called the suspend state, you can see when a process is blocked, it can also go to suspend state due to certain event, certain situation. And in the case where we don't have any ready state processes to run on the processor for a long time, the operating system actually can push out some blocked process to the disk. So the processors to run, they have to be on the memory, and memory has limited capacity. They have to be swapped to the disk. This means the hard disk or some secondary storage device. And then one of the suspended processes that are on the disk can be brought in back to the processor and activated so that they go into the ready state and can function as usual. So in this new, with the new suspend state, the state diagram slightly changes. Now we have 6 states, including suspend state. There can be different state suspension reasons. For process suspension, there can be multiple reasons. One is swapping. The OS needs to release sufficient memory to bring in a process that is ready to execute. And then there could be other operating system related reason. There may be a background or utility process or a process that is suspected of causing a problem. Interactive user request. A user may wish to suspend execution of program for purposes of debugging or in connection with the use of a resource. And then timing, the process may be executed periodically, an accounting or system monitoring process, and may be suspended while waiting for the next time interval. Then by the request of a parent process, the process may be suspended. To manage processes, the operating system needs to know 2 main things. One is the process's location and the process attributes. Process location, it means that the process will consist of at least sufficient memory to hold the programs and data of that process. The execution of the program typically involves a stack to keep track of function calls. Process attributes, the collection of program data stack and attributes is referred to as the process image. Process image location will depend on the memory management scheme being used by the operating system. The elements of a process image, the process image contains the user data, which is the modifiable part of the user space. May include program data, a user stack area, and programs that may be modified. Right. So another side note about the stack. So you might have heard of this word stack when you learn about data structures, and this is the same stack which implements the last in first out scheme. It's a last in first out, or LIFO data structure. So when you call functions, so remember, recall how you call functions in a program. So you have some execution phrase, execution sequence, and then you call a function. It has to jump to another location, and once the function completes, it has to come back to the previous location. So the stack is a data structure that helps us keep track of this function call. So when you have, let's say, 2 functions, function A and B in the program, first the function A is called, the execution has to keep track where the instruction was, or instruction execution was, before the function was called, because once the function A completes, it has to come back to that particular location where it was actually executed. Right. So while function A is executing, another function call happens inside the function A to a function B. Now function A's execution location should be saved on the stack, and the control goes to the function B. So once the function B completes, the operating system can go to the stack, push out the address where we stopped at the function A first, and then complete that, and then go back to the stack again, push the address where we were at the execution before the function A starts, and then finish the execution. So this is how it works So to facilitate this process, the function invocation process, we have this special stack area or the stack data structure in the process image. Then the user program means the program instructions to be executed, and the stack, each process has this LIFO stack, and process control block is the data needed by the OS to control the process. For process identification, we have identifiers, numeric identifiers that may be stored with the process control block. That include process identifier of this process, identifier of the process that created this process, that means the parent process, and some user who owns these processes. Then process state information includes the user visible registers, control and status registers, such as the program counter, the condition codes, and some status information, and the stack pointer. So stack pointer is some kind of a pointer which indicates the top of the stack. So stack is a data structure which I explained. It's a last in, first out approach of managing data. So you need to somehow have a stack pointer which indicates the top of the stack. So furthermore, we have scheduling and state information, such as the process state, the priority level. The process could be of different priority according to the scheduling scheme. Scheduling related other information and some event information. Then there could be some data structuring information, interprocess communication, some process privileges, some memory management pointers, and some ownership information, such as the file information that are required for the process. Process identifier is usually it is a unique numeric identifier. It's a number. When processes communicate with each other, the process identifier informs the OS of the destination of a particular communication. So using these numbers that identify different processes, we can do interprocess communication with the help of the operating system. When processes are allowed to create other processes, identifiers indicate the parent and descendants of each process. Process state and control information. So contents of the processor registers are user visible registers, control and status registers, and stack point. So we have a special register called the program status word, PSW, contains some condition codes, and some other status information. In some implementations of x86 processor architectures, we have a flag called eFlag. eFlag register is an example of a program status word used by any operating system that are running on this x86 processor architectures. Then we have process control information, the additional information needed by the operating system to control and coordinate various active processes. So this is a depiction of user processors. You can see what are the process control block information, and they have the user stack and some address space for having the programs and data, and there's a shared address space for these processes. There may be some shared address space. Sometimes you don't have a shared address space. Sometimes you may have. So typically, a process has its own memory space, which does not interfere with other process memory states, memory areas. The role of the process control block, which is the most important data structure is in the operating system, it contains all the information about a process that is needed by the operating system. Blocks are read and or modified by virtually every module in the OS. So blocks means the process control block in the memory. Defines the state of the operating system. When it comes to the PCB or the process control block, the difficulty is not accessing it but actually protecting it. A bug in a single routine could damage process control blocks, which could destroy the system's ability to manage the affected processes. So I introduced you the user mode and the privilege kernel mode in last time. So we have more information about those two modes. The user mode, like I said, is a less privileged mode. Usually is there for user programs to execute in. And the kernel mode or the system mode is a more privileged mode, also referred to as control mode, right? So for executing certain privileged instructions, you need to switch the system to the kernel mode. The process creation process, right? The steps in process creation includes assigning a unique process identifier to the process, allocating memory space for the process, initializing the process control block, setting appropriate links, and creates or expands other data structures as necessary. So this is the process creation steps. Then we also talked about interrupts, which is a way of disrupting the sequential flow of instructions in the in a computer system. So operating system has multiple ways of supporting interrupts, right? So one way of interrupting a process is interrupts, such as external to the execution of the current instruction, you can interrupt, and due to this asynchronous external event. So asynchronous means it could happen abruptly. So there's a reaction which is defined at the interrupt service routine. Then there's a mechanism called trap. So trap is also like some interrupt. Trap means a type of interrupt. Sometimes you can call it a type of interrupt. In a trap, it is associated with the execution of the current instruction. So you can trap the OS manually using these trap mechanisms. The program can create an interrupt, a trap interrupt, using the current instruction. Handling of an error or an exception condition is the use of traps. And the supervisor call means the explicit request. For example, call to an operating system function will also interrupt a process. So when it comes to switching between processors, right? So we talked about switching between processors. So there are different ways that switching can occur. If no interrupts are pending in the processor, when it is switching, process proceeds to the fetch stage and fetches the next instruction of the current program in the current process. Right? And if an interrupt is pending, the processor sets the program counter to the starting address of an interrupt handler program and switches from user mode to the kernel mode so that the interrupt processing code may include privilege instruction. So this is what happens when have interrupts. So when changing the process states, we first save the context of the processor, update the process control block of the process currently in the running state, move the process control block of this current process to the appropriate queue, and select another process for execution, update the process control block of the process selected, update the memory management and data structures, and restore the context of the processor to that which existed at the time the selected process was last switched out. So this is the procedure when you have a process switch and process changes states, right? So another side note, we have something called the process context switch. Process context switch means the current process that is running on the processor needs to be changed to a different process. So you have multiple processes in the ready queue, and the current running process needs to be suspended, and it goes to the ready queue, and another ready process comes into the process, or it goes to the block queue, it goes to the suspend queue, whatever it has to. If a process needs to be taken out of the execution or the running state, you have to save the context information like shown in this diagram. So saving it, loading the other process, and loading the context data into the processor is called the context switching, process context switching. So this process context switching is somewhat some expensive operation. Expensive as in it consumes a lot of operating system instructions, like it consumes a lot of processor instructions, so which could have been used for the actual execution of the programs, right? But process context switch is actually necessary for the operation of the system. Otherwise only one process will continue forever. So it's actually needed, but if you have too many blocking holes that block the current process, then there will be too many context switches, which kind of tarnishes the performance or degrade the performance of the computer system. Right, so we have now finished the part on processors. So we talked about the process states models, what processors are, and process control block, and the process life cycle. Now let's talk about another topic called threads. So threads is actually a lightweight process. So in the earlier computer systems or early operating system, there was no such thing called threads. We only had processors. So the operating system creates processors for each program, and maybe parent process can create multiple child processors, but that's it. But when we realize that mainly the process, if you want to have multiple work items within a program, you need to create multiple processes for handling each work item, which sometimes is not ideal. For one reason is that the processors don't have any shared memory space. If you take two processes, process A, process B, these two processes don't have any shared memory. So you cannot use any shared variables or anything. You have to have inter-process communication to talk to each other, which is a slightly complicated thing to do. So another reason is that if you have multiple work items in a program and you have to take turns, then you have to switch between these processes. And like I said, the process context switch is a very expensive operation in the computer system. So as a workaround to this, we have invented something called threads, which is actually a lightweight process, and there are many threads within a process. So you have the process, and within the process you have small like minor processes, so sub processes kind of thing we call threads. So threads share the memory space of the process that they are contained in. So threads within the same process share the memory space of its processor. So if one thread creates a variable in this shared memory space, another thread in the that in the same process can see that variable. So there's a shared variable. So communication is easier. So there could be processes with one thread or many threads associated with it. So here is a depiction of single versus multi-threaded processes. You can see one process, one thread, one process, multiple threads, multiple process, one thread, and multiple process, multiple threads. So all these combinations are possible in the operating system. But back in the day, there were only one process, one thread systems. And now we have multi-process, multiple thread systems. So the thread also contains some information like the processes. We have the thread context, right? And an execution state, an execution stack also there. The stack is for per thread. We have stack, but there's a memory space that is common to all the threads in the process. Some per thread static storage for local variables are also available. There can be some thread local variables. There can be some process local variables. So thread local variables might not be visible to other threads, and the process local variables will be visible to all the threads in the same process. Access to the memory and resources of its processes shared with all other threads in that process. Threads within the process, you can see in the single threaded process model, we have the only one thread, right? Only one thread. So one PCB and the user address space is there, user stack is there, kernel stack is there. In the multi-threaded process model, you have multiple threads within the same process. So one process control block has control information for all the threads, and the user address space is shared. That's what I mentioned. The user space, the memory is shared between all the threads. But each thread has a thread control block and a user stack and a kernel stack specific to that particular thread. So benefits of threads, because they are lightweight, the creation time is very less. So it's not as expensive as creating a process. And also you can terminate it fast. Thread context switch is much faster than the process context switch. I already explained this, and inter-thread communication easier compared to inter-process communication. Right now, when the processor actually wants to execute these processes and threads, to the processor, how the threads from the user space are visible determines how they are treated. Right, so the processor sees certain threads or processes in the user space, and then how they are seen by the processor determines how they are actually treated by the processor. So at the user space, whatever happens is actually not visible to the processor. So the processor only sees the kernel space thing. So kernel space is this privileged space where the OS functions happen, right? So the programs usually run at the user space, user program. So you can create many threads at the user level, and the processor will not see them. So to execute user space threads, you need to map them into a kernel space thread. Right? So the kernel space threads are visible by the processor. So one model is this shown here. It's called the pure user level thread model. In the pure user level thread model, you can create so many threads using a thread library on the user space or on the program. But when it is executing, all those user level threads are only mapped to one kernel level thread. So this kernel level thread is the actual one that is executing on the processor. So all these threads at the user space have to take turns being associated with the kernel thread. Right? So the kernel is not really aware of the existence of the user space threads, whatever happening. So for example, let's say we have one process at the user space, and this user process is just one. It is allocated to a processor. So the kernel space, you can see that process, and within the process there are many user level threads. So with user level thread libraries, like maybe something like pthreads library or some Java threads threading library, Python threading library, you can create threads, right? So with the user level threads, you can do various work assignment at the program, but the operating system doesn't care, or the processor doesn't care. It only can see one process. So there is only one time slot in the that timeline given to that particular process, and that within that one time slot, you have to manage all the work belonging to all these threads, user level threads, right? So the thread management, how much time actually is given to each thread from that processor's time quantum, time slice given by the operating system is managed by the user level thread library. Then we have kernel level threads. So in this case, you have more than one user space thread. I mean, the user space threads are mapped into a kernel level thread. So user space, you have one user level thread, and the kernel space has one kernel level thread mapped to that user space. So now the processor sees all these kernel level threads, and so that the user level threads are also seen. So the processor will give treatment, the fair treatment to all the user level threads in this manner. So the thread management is actually done by the kernel, because the kernel, the operating system, has information about the user level threads, and each user level thread is mapped to a kernel space thread, and the kernel space threads are visible to the processor. So each of these threads will get its own time slice from the OS itself when the processor is executing. So unlike in the pure user level thread model, in this case you don't have to share the same small process time quantum within the all the threads, because each thread is mapped to a kernel space thread, and each thread will get its own time quantum. So there is no thread management code in the application level, simply an API to the kernel thread facility. So if you compare the user level and kernel level threads, user level threads thread switching does not need kernel privileges. Scheduling is done by user level thread library, and there is high portability, and because these are managed by user level thread libraries, you can install that library in any operating system and should be able to run the application. Pure parallel execution may not be possible. Now you should understand why. And terminating blocking, one thread will block the block or terminal all threads in the process. So if you remember, the operating system only sees one process, only one process, although there are many threads in the same process. So if one thread within that process causes any problem, the processor will see that, okay, from this process there's some problem, and it will fully suspend or block, terminate that particular process, the whole process. So all the threads will be blocked or suspended. When it comes to kernel level threads, the kernel can simultaneously schedule multiple threads from the same process or multiple processors, because operating systems see all the threads as individual elements, not as one process holding many small threads. So you can give one, you can utilize the multiprocessors. If you have multiprocessors, you can have them parallelly executing, or you can give better scheduling to threads, because the kernel sees all the threads coming from the processes. If one thread in a process is blocked, the kernel can schedule another thread in the same process. So no problem. You don't need to block the whole process like in the user level thread. Kernel routines themselves can be multi-threaded, and the problem is the kernel level threads are always dependent. There's a less portability. There can be some combined approaches as well. Some systems allow combined approaches where you have some user level threads like shown here. So you have multiple kernel threads allocated to few threads. So it's some kind of a multiplexing approach. You have, so in this example, you have 3 thread library threads that are mapped to 2 kernel threads, and we have 1 user space thread which is directly mapped to 1 kernel space thread. So it's a combined or hybrid approach. So this kind of hybrid approaches are well used in today's systems instead of going for pure kernel or pure user level threads. Right. So we have come to the conclusion of the today's week 2 lecture of the computer networks and operating systems course. So we talked about processors and threads in today's lecture. The process is a structure that helps with resource management, and there are different state transitions. So we studied different thread models, transition models, state models, the 2-state, 5-state, 6-state models that help us understand the state transitions. Then the process control block holds information about a process in the memory, and the process is scheduled on the process of execution. The exact scheduling process we will discuss in the next lecture. And threads are some sort of lightweight processors. A process may contain one or multiple threads. Okay, a process may contain one or multiple threads. So I showed small typo in the slide. User level versus kernel level threads. We did a small comparison, and what are the consequences of user level, and what are the good things, what are the bad things about user level and kernel level threads. And we also saw what are the mapping schemes that map threads with processors. We have PO user level thread model, a PO kernel level thread model, and we have some kind of combined or hybrid thread models. Map the threads with the processors so that the processor and the operating system see them differently at the kernel level. Right. So that's the end of the second lecture. I will see you in the third week lecture. Thank you very much.